Good day, everybody. Here we're going to be working in this video with special right triangles, of which there are two types, and we're going to focus on one of them. We're going to focus on what are called 45, 45, 90-degree right triangles, and you're going to be finding unknown side lengths in those triangles and applying the relationships between the sides of 45, 45, 90 triangles to find a lot of various measurements and so forth. You'll see what I mean as we go on. And I want to start off with talking about 45, 45, 90s in the context of why are they special. Now, one thing I hope you know about a triangle that has a 45 degree, a 45 degree, and a 90 degree angle is that it's an isosceles triangle because it has two congruent angles, and B, it's a right triangle because, well, it's got a right angle. So an isosceles right triangle is what we are referring to here. And you can imagine, without me giving you much explanation, why an isosceles right triangle might be a special type of right triangle. But an additional property that makes a 45, 45, 90 triangle special is that it's half of another special figure, the one you see drawn on your screen right now, a square. Because you can always create a 45, 45, 90 triangle by a pair of them actually, by drawing the diagonal of a square. Now, what I'm wanting to do in the beginning of this video here is I'm wanting to show you what the relationships between the sides of a 45, 45, 90 triangle are. Okay. Now, why does a square have to have 45, 45, 90 triangles when you draw a diagonal? Well, all the sides of the square were congruent to one another, right? So these two sides were congruent, which means these two angles must be congruent. And since this is a right angle, again it was a square, that means the two acute angles each have to be 45 degrees. Alright, now suppose that we didn't know the exact length of the side of the square. We, in other words, just called it x. What I'd like to do is have us find out what are the other missing side lengths if I know that one side of this 45, 45, 90 triangle is x. Well, part of that is going to be it's going to be easy because the legs of a 45, 45, 90 have to be equal to one another, right? Well, now let's work on finding the hypotenuse with methods that we've already learned in this chapter. And in particular, what we're going to have to use is the Pythagorean theorem because we know two of the three sides of a right triangle. Now, let me just call this D so we have something to call it. D for diagonal. If I wanted to show what the diagonal is here, using Pythagorean theorem, well, we would start off by saying D squared is equal to x squared plus x squared, right? There's your C squared, your A squared plus B squared. Alright, now, since both those sides A and B were equal to one another, we can add their distances together like this. X squared plus x squared is going to give us 2x squared. Now you know that in order to find the length of D, we're going to have to take the square root of both sides, and that will give us D equals the square root of 2x squared. I'll try to teach you a little bit about operations with radicals in this video as well. Whenever you take the square root of a product, such as 2 times x squared, you can divide that up into the product of the square root of each factor in that product. So you can make that the square root of 2 times the square root of x squared. And I'm going to rearrange the order of this, but the square root of x squared, you ought to know, is just going to be x. And then the square root of 2, well, we don't know that. It's going to be the square root of 2. Okay. And so I'm trying to make a point here. You can, if you like, every time you have an isosceles right triangle, go ahead and use Pythagorean theorem to find out what the third side is. But notice what this expression right here kind of tells me about the relationship between the hypotenuse and the leg. And this works every time because I did it for an unknown value, x. All you have to do is take the side length of a 45, 45, 90, of the leg of a 45, 45, 90, and multiply by the square root of 2 in order to find the length of the hypotenuse. Let me write that down because that's an important thing. But I'm going to write it down on the next slide. Whenever you have a 45, 45, 90 triangle, which you will know you have every time you have an isosceles right triangle, there are two relationships that I need you to know. Alright, first of all, the legs are equal to one another. or rather the lengths are equal and the legs are congruent to one another. Secondly, the hypotenuse is always, its length is simply always equal to the length of a leg being multiplied by the square root of 2. Only works for the 45, 45, 90 triangles, but that's a fact worth knowing. Let me write that out in words. All right, I'll abbreviate it a little bit, but the length of the hypotenuse equals the length of the leg times the square root of 2. All right, very simple thing. Let's put it into practice right now. I want us to find the value of each variable in these two triangles. Now, I didn't specify, and I need to, that these are 45, 45, 90 triangles. Let me put an angle measure in each of them. I would never want you assuming that they were 45, 45, 90 triangles just because they looked like it, so we need that angle measure there. All right, now in part A, you see I gave you the length of one of the legs, and I'm asking you to find the length of the other leg and the hypotenuse. And it's as simple as this. So let's not bother with Pythagorean theorem. We know x has to be equal to 7 because the legs are equal, and we know that the hypotenuse has to be equal to the leg times the square root of 2, and that's it. All right, we knew both sides of that triangle. Similarly, in part B, we're given the length of the hypotenuse, and we're trying to find the lengths of the two legs. Now, one thing that I know here is that P and Q have to be equal to one another because they are each legs. We'll have to do a little bit of reasoning here. You would multiply the length of either P or Q by the square root of 2 in order to find out what the hypotenuse is. So, how can we kind of reverse that? Well, if you know the hypotenuse, you divide its length by the square root of 2 in order to find the length of the leg. All right, another way of looking at this is you could have written this. The leg P times the square root of 2 is equal to the hypotenuse, 24. And then if you solve that equation for P, it would be what I have right here, right? So divide the hypotenuse by the square root of 2 in order to find the length of the leg. Now, remember that you can't leave radicals in denominators. You're not supposed to do that. And so one of the things I need to do with this answer is I need to go ahead and rationalize the denominator, which with square roots you could do by multiplying by the denominator over the denominator. Hopefully you kind of have the background in your head as far as how that works. And that will give me 24 square root of 2 over 2. Now, the square root of 2 times the square root of 2 gives you the square root of 4. And the square root of 4 is 2. That's where that's coming from. And then anytime you can simplify the numbers outside the radicals like you would in any other fraction, you go ahead and do that. 24 over 2 is just 12, so that's 12 square root of 2. Good. A couple more problems here involving 45, 45, 90 triangles. In this one, I want us to find the length of the diagonal of a square whose perimeter is 52 square root of 2 centimeters. All right, well, first thing we need to do is draw a square, of course. So there's our square. And then let's go ahead and draw its diagonal. All right, so again, D for diagonal. And what we're told is that the perimeter of the square is 52 square root of 2 centimeters. All right, well, the challenge here is going to be, can we find the length of the legs? And then once we know the length of the legs, can we use that then to find the length of the diagonal? Of course we can do that. And the way you use perimeter to find the length of the legs is you go ahead and divide by 4, right? There's 4 equal side lengths. So if I call this S and I call that S, because they are equal, I could say that the side length is equal to 52 square root of 2 divided by 4. Now with division with radicals, you don't ever divide what I call inside numbers, radicands is really what they're called, by outside numbers. Okay, that's not underneath the radical. But you do divide outside numbers by outside numbers. 52 divided by 4 is 13. So you get 13 square root of 2 is the length of each side. Now let me put that in there. And then since it is a 45, 45, 90 triangle, we know that the hypotenuse, which in this case is D, is equal to the length of a leg, 13 square root of 2, multiplied by the square root of 2. Okay, there's the length of the leg. There's that times the square root of 2. Now, 13 square root of 2 times the square root of 2 is going to end up becoming 13 times 2. We've already talked about what the square root of 2 times the square root of 2 is. And that gives you then 26 centimeters is the length of that diagonal. Alright, one more problem for you. This time, I want you to find the area of an isosceles right triangle whose hypotenuse is 14 square root of 6 millimeters. Well, let's draw an isosceles right triangle. There's that, and we know the length of the hypotenuse is 14 square root of 6 millimeters. Alright, now I want to remind you of something I told you in a previous video. Whenever you're trying to find the area of a right triangle, it often makes sense to use one leg as the base and the other leg as the height, because they're perpendicular to one another, so they can work that way. So really all we need to do then is find the length of each leg, and then we can use 1/2 times the first leg times the second leg in order to find this area. Alright, well, so how will we go about finding the length of the leg? If we just call each of those x for right now, two ways of thinking about this. Alright, if you want to write out a full equation, you know that a leg times the square root of 2 equals the hypotenuse, so you could write x squared root of 2 equals 14 square root of 6. Now you can skip that step if you just reason out in your head that you divide the hypotenuse by the square root of 2 to find out what the value of the of the leg is. So 14 square root of 6 divided by the square root of 2. Now we're not going to rationalize this denominator yet because you can divide inside numbers by inside numbers, radicands by radicands. The square root of 6 divided by the square root of 2 is the square root of 3, so this becomes 14 square root of 3. That's the length of each leg. Now as far as the area goes, we're doing 1/2 times base times height. Then I already told you that we're going to use the legs as the base and the height. And since those are the same as one another, we could really say, rather than writing out 14 square root of 3 times 14 square root of 3, that we are squaring 14 square root of 3, right? This is the base times the height right there. Now, how do you square a product like this? Well, you square each factor in the product, so that becomes 1/2 times 14 squared times the square root of 3 squared. I'll bring the work up over here. Now 14 squared, you may know, is 196. The square root of 3 squared is going to be equal to 3, because the square root of 3 times the square root of 3 is the square root of 9. Gives you 3. Alright, and then half of 196 is 98. 98 times 3 is 294. We got 294 square millimeters is the area of that triangle. Alright, so you've got a pretty good look at how you use 45, 45, 90 triangles and your relationships between their sides here to really save you some time. Especially these last two problems would have taken forever if you'd have needed to use Pythagorean theorem. We shortened them greatly by using those 45, 45, 90 triangle relationships. Hopefully you learned a little bit about operations and radicals along the way as well. Thanks for your attention. Good luck with these problems. I will see you in the next video. Bye.